This is 2758. It says you have a long, straight cylindrical wire on the x-axis. So we can draw that. Let's see. There's x, and we'll put one face here at the origin and let it move out. And it goes to a length L. So it goes from 0 to L. And let's see, it has a resistivity rho, and it obeys Ohm's law. And what else we know? It's at a potential V at x equals 0. So here it's at V, and presumably that's plus V, but we'll assume it's plus V, and it's at 0 at the position L. So the potential difference is then just delta V, or the potential difference delta V is just equal to V, as they've defined it. Let's see, it has a diameter D, right, so if we want to think about areas and things, we would use a diameter D. So the first question is, let's see, the magnitude and direction of the electric field in the wire. So for this part, you got to remember that we can always say that that the E field is the rate of change of the potential. So the potential is going from a high value to 0 across the length of the wire. So E is going to be what? The magnitude is just going to be delta V over L. Okay. There's lots of negative signs this way, that way. Are we going from A to B, or A to B, or B to A, or whatever? In this case, we can just get it by looking at it, because we know two things. We know the magnitude will be delta V over L. Plus and minus don't matter. And the direction we can know just by looking. You know, if this is the positive V, if this potential is higher than this potential, then the E field is going to go this way. If you put a test charge in this material, it will fly this way, because it will go away from the high potential towards the low potential. So rather than worrying about whether we're going from A to B or B to A and the minus sign and all that, we can basically just say that the potential of the E field is V over L. Right? The change of potential is just V, because we're going from 0 to V. And it happens over a distance L. And we know it's going this way in positive x, so we just put I hat on there. So it's positive x direction. So the E field then for part A, magnitude and direction is V over L, I hat. Let's see, B, the resistance of the wire. Alright, well we know resistance of a cylindrical wire is always R equals rho L over the area. And this pretty much obeys that rule. There's nothing unusual about this. It's just a wire with a resistivity rho that obeys Ohm's law. The only thing is, if we want to get it in terms of the actual parameters given, the D, we need to replace the area with the diameter. So that's pi r squared, but in terms of diameter, it's pi d over 2 squared. So that's d squared over 4 on the bottom, so we just bring the 4 to the top. So it's 4 rho L over pi d squared. And then we have the resistance R in terms of things that are given. Let's see. It also asks for, let's see, C, the magnitude and direction of the current, of the electric current in the wire. Alright, so for the magnitude and direction of the electric current, so it says that it obeys Ohm's law, right? So it obeys delta V equals the total current times the resistance. So we know, again, delta V is just V, because it's going from 0 to V, so the change is V. Okay. And we're looking for the current, so we'll leave this just as I. And we can write down here 4 rho L over pi d squared. 4 rho L, oops, over, dramatic there, pi d squared. So to just solve that, for the current is just, way to solve for the current. The current is V pi d squared over 4 rho L. And the direction it's going to go, well, since it's going to go in positive x, because we have the high potential here and the low potential here, current flows from high to low potential. So we can say positive x direction. We aren't going to write it as a vector, it just asks for the magnitude and the direction. So we don't usually call current a vector. Let's see, that was C. It also asks for the current density in the wire. So D. Current density, of course, is just the current over the area. So we're going to take this expression and divide it by the area. V 4 pi d squared, V pi d squared over 4 rho L. And now we've got to divide by the area. Perhaps you can see that the area is already in here. You're really just going to pull out that pi d squared over 4. If we put the area down here, it's pi d squared over 4, and the 4 comes up here, and this just all cancels out. The area was already sitting in there quite nicely. So J, the current density, is what's left, V over rho L. And again, if we want the direction, it's in the positive x direction. Same direction as the current. And the last question is show that E equals rho J. Basically they're saying show that this obeys Ohm's law. Well, it's true. We already have that J is V over rho L, and V over L is the magnitude of the E field. We go all the way back over here. So J is the current density is the electric field divided by rho. So one substitution and we have the answer to E. And that is Ohm's law. Now that's not exactly how we wrote it on day one. Remember that rho is 1 over sigma. So another way we might write it is J, oh wait a minute. I'm sorry. Okay, so here we have solved for J. J is E over rho. The question for part E, sorry, I got ahead of myself, is E, what is E equal to rho J? This is what they want you to prove. So we did. Made a substitution to get E, we got this, and we just rewrite it. E equals rho J. This is the thing part E said to show. And then what I was going to say is, since this resistivity is 1 over sigma, we also know that J, the current density, equals sigma times E. And I just wanted to remind you of that. That's how we originally wrote Ohm's law. If you apply an electric field, you get a current that depends on the conductivity. Completely equivalent is the current density you get is the electric field over the resistivity, or you can write it this way. They're all the same thing. Okay? That's it.